All right, so it's 10. We'll get started. So just a reminder of what we talked about on Wednesday is we were talking about thermal energy for the most part and how we can transfer or calculate the energy that is transferred between materials based on the mass of the material, the specific heat constant of the material, and the temperature of the material. So we looked at that calculation. That was the last thing we did on Wednesday. What we're going to talk about now to begin with is pressure volume work. So Wednesday was heat. Today we're going to look at work due to changes in pressure and volume. And the calculation for this is relatively straightforward. Work equals negative pressure multiplied by the change of volume. And for this, the tricky part is converting it into joules, or to remember to convert it into joules. Because remember, when we talk about energy, the SI unit of energy is the joule. Here, our conversion is 1 atmosphere liter. So doing this calculation, pressure should be in atmospheres. Your volume should be in liters. So 1 atmosphere liters is 101.3. And just remember, this delta here is final minus initial. So it's final volume minus initial volume. So let's think about what this means and actually turn to work and kind of go back to what we were talking about on Monday and Wednesday when we were talking about work. So if a gas is expanding, that is, the volume is getting bigger, it is doing work. So delta V is positive, which means work is negative, right? Because this negative sign here. However, if a gas shrinks, work is being done on it, right? So the volume is negative when it shrinks, which means the work is a positive value, which correlates exactly what we talked about on Monday and Wednesday when we were talking about the balloon example. If your balloon's expanding, you're doing work, so work is negative. If a balloon is shrinking, work is being done on that balloon, so work is a positive value there. Right, so any questions about those ideas before we jump into the math? All right, so here's just a quick question to see if we understand this. So we have a piston, and this piston absorbs 565 joules of heat, and it expands from 0.1 to 0.85 against an external pressure of 1 atmosphere. Therefore, what is the change in internal energy? And is this endothermic or is this exothermic? So take a few minutes here at the beginning, try to do this math, and let me know if you have any questions. Otherwise, I will be back to work this out in a minute or so. All right, since we have quite a bit to cover today, I'm gonna go over how to solve this. Hopefully you had a little bit of time to at least like declare your variables and get a sense of what's going on here. So work equals minus P delta V. So that is equal to minus 1 atmosphere multiplied by final volume, which is 0.85, minus initial volume, which is 0.10, which is negative 0.75, and these are in liters, atmosphere liter. Then I wanted to convert this to joules because when we're working in energy, we need to be in joules. So 1 atmosphere liter is 101.3 joules. Atmosphere liter at the top, bottom, cancel out. So overall, the work is negative 75.975 joules. For sig figs, it should only be 2 sig figs. So it would be negative 76, really. Why is the 0.75 negative? It's negative because there's a negative sign in front of the equation. So 1 times 0.75, which is this, then you just put a negative sign there. Yeah, that is the conceptual answer. It's expanding, so it's doing work, so it's losing energy to do that. And it's, yeah, so that is the correct conceptual way to think about it. So that's the work portion of energy. So that's our W. Our Q, well, it's absorbing heat. And that actually, I cannot draw a balloon to save my life. But that goes with our second part, is this endothermic or exothermic. So thermic means heat. So it's going inside. So this is an endothermic process. That means heat is positive. So this is 565 joules for my heat minus 75.975 joules of work. Overall, my change in internal energy is a positive 489 joules. So this was my Q. That's my W, and it's an endothermic process because it was absorbing heat. So there, whoops. So there's an example of how we can calculate work by looking at a change of volume. Is there any questions about this calculation, about what we did here? All right. Now we can move on. Here we have a combustion question, but I think I'm going to skip question 4. So we're going to skip this because we actually are going to talk about combustion here in a second on our new slide. So just remind yourself when you are studying for the test, we won't look at something like question 4. So for the second time, we're going to skip this and move on to our next PowerPoint, which I should have posted like an hour ago. So let me just switch over to that now. There we go. And our next topic we're going to talk about is called calorimetry, and specifically bomb calorimetry. Now, if you've ever wondered, like on the back of food, how they know how many calories goes into like a certain amount of food, like how do I know a Snickers bar is 180 calories per serving? One way you can figure that out is through bomb calorimetry. Now, what bomb calorimetry is that you take a substance and you put it inside this container. This container is called a bomb. And what you do is that you blow it up. And when you blow it up, you have this bomb, the actual bomb's right here in the middle. You have it surrounded by water. And you measure what was the change in temperature of the water. And by measuring the temperature change of the water, you can back calculate to know how much energy was released by blowing up that molecule, by using the idea of when blowing up the molecule, you'll release heat. That heat has to be absorbed by the water. Now, water is not the only thing that is absorbing the heat here. The calorimeter, the machinery, is also absorbing the heat, so we have to account for that. And we account for that by the heat capacity of the calorimeter, or a calorimeter constant. This is the same idea as a specific heat constant. We're just saying that the calorimeter itself will heat up when you explode something in it, and we can calculate how much energy it takes to heat up that calorimeter itself. So here, let me talk about what these calculations say in plain English. We're saying that the heat absorbed by the calorimeter after blowing something out is equal to the specific heat constant of the calorimeter. Remember, that is how much energy does it take to raise the temperature of a certain amount of stuff. The stuff here being our calorimeter, multiplied by the change in temperature we are measuring, because we have a thermometer in this machine. And this heat must have came from our reaction of blowing up our substance, because that's the only place this heat came from. And from our discussion earlier this week, if a system absorbs energy, it must come from the surroundings. So that's why we can say that the heat we measure in the calorimeter is equal but opposite sign to the heat of our reaction, which was blowing something up. Therefore, the change in energy inside of our system, here our Snickers bar or our sample, must be equal to the heat released in our reaction. So that's why there's no negative sign here. They're basically the same thing. One more point to talk about for this bomb calorimeter. Up to this point, we've always talked about delta E equals Q plus W. Here, though, we're just saying delta E equals Q, because this is a constant volume calorimeter, right? And based on what we just looked at this morning, we said work equals negative P delta V. However, if it's constant volume, final volume equals initial volume. So let's say this had a volume of 1 liter, right? So my final volume at the end of this experiment is 1. My initial volume was also 1 because it's constant volume. Therefore, our work equals 0. because there's no change in volume. That is why we can say, okay, all of the change in energy must be due to heat. We measure that heat using a thermometer. That, in essence, is how a bomb calorimeter works. And if any of you ever go on to physical chemistry, you will do actual experiments with a bomb calorimeter where you blow stuff up and you just measure, okay, how much energy was released. But before we move on to doing some calculations, does anybody have questions about the theory of this instrument or what I was saying there? Anything at all that I can help make more clear if possible? All right, so let's actually look at some calculations for this. So mothballs, they stink, but I guess they're effective, are usually primarily made of the hydrocarbon. And don't worry if you don't know what hydrocarbon means. It just means carbon and hydrogen compound. And it's made out of naphthalene, which is C10H8, that has this molecular weight. So if you burn 1.025 grams of naphthalene in a bomb calorimeter, you find the temperature rises from initially at 24.25 to 32.33. What is delta E reaction for blowing up naphthalene in units of kilojoules per mole if the specific heat capacity of the bomb determined in another experiment is 5.11 kilojoules per centigrade? So here's the equations you need to do. And there's a lot of moving parts. So let me just help you before I let you go at it, just to do some do some variables. So here, 5.11 kilojoules per C, that's the heat capacity of the bomb calorimeter. That's C cal. Temperature rises from, so this is temperature initial, INT, to temperature final, FIN. Don't forget kilojoules per mole. That getting it per mole might be tricky, but see how far you can go with this. Again, these are the equations you want to use. If you get stuck at some point or not quite sure how to even begin, let me know. Otherwise, I'm going to give you a few minutes to see if you can work this calculation out. All right. So again, since we have quite a bit to do, let's take a look at this. So the thing I think that people struggle with these type of questions is the sheer complexity of what these questions say and trying to like piece your way through each calculation. The calculation themselves are rather simple, but actually figuring out, okay, what is this saying and what is this trying to tell me? Is quite can be quite confusing. So that's why I kind of worked out the variables for you. So let's take a look at this. So the first calculation, QCal equals CCal, which is 5.11 kilojoules per degree centigrade, multiplied by temperature final. Remember, delta T is always final minus initial. So 32.33 minus 24.25, which they're going to have, I'm going to put the C out here just because I didn't want to write it twice, but that has a unit of centigrade or Celsius. So Celsius cancels out. So QCal will have a unit of kilojoules from our bomb calorimeter constant there. When you do that, let me move my Excel sheet so I can actually write. QCal equals negative, or not negative, I'm not at that point yet, 41.2888 kilojoules. And let me just do the sig figs here really quick. So I have to do the subtraction myself. Okay, so that will have 3 sig figs because when you do 32.33 minus 24.25, that answer is 8.08. So those 3 are significant, so 41.3. So that's QCal. That was the heat absorbed by the calorimeter. Well, where did that heat come from? It came from exploding our naphthalene. Do we not wait till the end to do sig figs? You do wait till the end to do sig figs. That's why I just put the bracket there as a way to like remind myself, okay, at this point in the calculation, that 41.28888, that has 3 sig figs in it. That's a way I keep track of it because I'm gonna use that number here in a minute again. But yeah, you generally don't want to round before the end. So that's our QCal. And all of that heat came from blowing up naphthalene. So Q reaction, our explosion, is just negative. And here's a little tip for everybody to, as a way to check yourself. When you're exploding something, that generally releases heat. I would hope so. I've never heard of a bomb that makes everything colder around it. So since you're releasing heat, heat should be negative for explosions. So heat is negative 41.288 kilojoules. However, I want this in kilojoules per mole. And I think this is a point where people can get stuck. Like, how do I put moles here? And it's simpler than you probably think it is. So I just need to divide this by moles. That's what I need to do to get my final answer here. QCal and Q reaction are the same. They're the same but opposite sign. Remember, in this instrument, we are having material, here's naphthalene, and we're lighting it on fire, and we're measuring the change in temperature of our instrument. Therefore, any heat absorbed by our instrument must have come from our reaction. That's why those numbers are the same, but opposite sign. One is absorbing that heat. The other thing is releasing that heat. Yeah. Right, so I need to get this in kilojoules per mole. Well, in my experiment, I burned all this heat came from 1.025 grams of naphthalene, which using my molecular weight, 128.17 grams for 1 mole, grams cancel out, that is 0.007997 moles for sig figs. So that is how many moles of naphthalene I burned to get this amount of heat. So what you do is you just take your number in moles, you put that on your denominator. Because your units are now kilojoules per mole when you do that. So if you have the right units, you probably did the calculation right, which means that the explosion of naphthalene is negative 5162 whoops, I wrote that wrong. Negative 5162.91 kilojoules per mole. Look at sig figs. This has 3 sig figs. This had 4 sig figs. So my answer should be 3. So I'm going to switch to scientific notation. Take my decimal, move it over 1, 2, 3 spots, which is negative 5.16 times 10 to the 3 kilojoules per mole. What this number means is I get this much energy for every mole of naphthalene I burn. That is our final answer. And yeah, getting it from kilojoules to kilojoules per mole, that's definitely tricky, because you probably think you have to do something complicated. All you have to do is divide it by how many moles you had. That's it, once you get it in kilojoules. So any questions about our calculation of calorimetry here? How much energy is released when exploding naphthalene or burning naphthalene? Any questions about what I did there mathematically? Make this fun. Well, I tried to make it easy to follow. If it's fun, that's just a bonus. All right, if there are no questions, we can move on then. Now, let's look at how you will actually do calorimetry inside Gen Chem Lab. Bombs are like really expensive, and they're really precise instruments that we can't just give to Gen Chem 1 students. We can't have like 20 or 30 bombs laying around. So what instead you would use is what's called a coffee cup calorimeter. Those of you who have taken general chemistry in high school, you might have done something like this. But the idea here is the same as the bomb calorimeter. But here we're not exploding anything. We're doing an actual chemical reaction. So we have 2 styrofoam cups and a lid. And we're going to assume that no heat is able to penetrate or leave these 2 coffee cups, right? So that's our assumption. We then have some kind of chemical reaction happen in here, and we stir it, and we measure the change in temperature of our reaction. Since this is constant pressure, we're going to do the same trick of saying, there's no work being done. It's only heat. So all of our energy that's being released is due to heat here. And so let's look at this math as the same idea. Our reaction, the heat of our reaction is equal to the negative heat of our solution. That is what we're measuring. And on Wednesday, we looked at how to measure the heat of a solution or any substance. It's the mass of that solution multiplied by specific heat constant multiplied by delta T. Now, when doing this calculation under constant pressure, we get to do something fancy that will take some lines of math to actually show that we don't actually care about in Gen Chem 1. We just care about that at constant pressure, this Q just changes to an H. So what is H? H is what's called enthalpy. And I could probably talk, for a couple lectures on the physical chemistry background of what enthalpy means. For you just need to know enthalpy is a fancy way to say Q. Enthalpy and Q mean the same thing under constant pressure conditions. Enthalpy is heat. H is heat. So that's what we're calculating here. Once you get into your higher levels of chemistry, if you take your higher levels of chemistry, then you'll dive into like, what does delta H actually mean? Why is it important? Right now, we're just introducing delta H for you. So once you calculate Q reaction, you automatically calculate delta H reaction because it's the same thing. And usually people are interested in enthalpy per mole, delta H per mole. And so you just do the same thing we did on the last problem of when you get your energy, just divide by how many moles you had in your reaction. So that is your coffee cup calorimeter. That is the background of the experiment you will do at some point in lab. I believe we're still doing that experiment even in these COVID times. I know normal semesters we do that. So here is another wall of text that will look intimidating when you first read it. But again, you want to just simply break it down piece by piece and start labeling your variables and work from there. So instant cold packs, I mentioned those on Monday, I believe. How they actually work is that you have two substances. You have ammonium nitrate, which is a salt, and you have water. And these are separated by a very thin piece of plastic. To activate the cold pack, you break the plastic barrier, allowing the salt and water to mix. When they mix, heat is being absorbed. Now, I want to know what the enthalpy change is for this reaction. So I did coffee cup calorimetry. I took 1.25 grams of my ammonium sulfate, molecular weight given here, and it's dissolved in 25 milliliters of water. If the initial temperature of the solution was 25.8, and the final after dissolving the salt is 21.9, what is delta H, or the change in enthalpy? Remember, delta means change, H is enthalpy. What is the change in enthalpy in kilojoules per mole? Some things you'll need is that the density of the solution is 1.02 grams per mil, and the specific heat capacity of the solution is 4.184. So a lot of numbers, a lot of variables. The equations you want to use for this are up here. Try to see how far you can get with this. Just a hint. Remember, this is solution, so it is not mass of salt. We are measuring the change of our solution here, and that's where density is going to come into play. So those are your hints to get you started. And again, I will give you a couple minutes. Try to go through this. and I will be back with the solution. If you have questions, please let me know. All right, so hopefully you had just a little bit of time to start assigning your variables. Probably not all the way done yet, and that's fine. Again, I'm just kind of rushing here a little bit to make sure we don't fall too far behind. So let's start calculating Q solution. And it's very important that we remember that it is solution. So the first thing I need to do is mass of the solution. Well, I have 25 milliliters of the solution. And from my density, 1 milliliter of a solution is 1.02 grams in weight. So the mass of my solution is 25.5 grams. So I pointed this out at the very beginning, but I do want to point out again, make sure that you are connected to what the equation actually says. Because I know if I was to give this on a test, there's a fair portion of people who would see gram here and say mass gram. Okay, the mass is 1.25, but again, we are measuring solution, not how much solid I put in there. So let's do this. So Q reaction, which is what I'm trying to actually figure out because I want the enthalpy of reaction. Whoops, I cannot draw a line. And kilojoules per mole, which is Q reaction. So Q reaction equals negative mass of solution, 25.5, multiplied by the specific heat capacity of the solution, 4.184. And this is in grams. This is joules, gram, centigrade. Grams cancel out. Grams at the top, grams on the bottom. Multiplied by my change in temperature, final minus initial. So my final temperature is 21.9 minus my initial temperature, which is 25.8, which makes sense because this is supposed to be cold. Celsius cancel out. And before I do this, when you actually do the parentheses, it's negative 3.9. So that's going to be limiting my sig figs. So my answer should have 2 sig figs because of that. So my Q reaction then is 400, whoops, decimal too early, 416.098, 2 sig figs, joules. That's my unit here because the only thing left is joules. Now there's a couple things you can do from here. You can convert this into kilojoules right away. But the thing I did was I need to find out, okay, how many moles were in my reaction? Remember, my reaction here is dissolving my salt, right? That's the reaction. So the moles is how many moles of salt did I add? So I'm going to do that right near my reaction here. So I have, let me move my Excel out of the way so I can actually see what I'm doing here again. So I have 1.25 grams of sodium nitrate. And my molecular weight is 80.043 grams per mole for 1 mole. Grams cancel out. So the number of moles I have are 0.0156 moles of ammonia nitrate. Then I look, okay, I want kilojoules per mole. Right now I have joules and moles that are separate. So let me combine those two. 416.098 joules divided by how many moles I had, because I want kilojoules per mole eventually. So right now I'm making joules per mole. 156 moles. That is 26,644 joules per mole. And the last thing is I want it in kilojoules per mole, not joules per mole. So I need to convert from joules to kilojoules, which is something we did way back, like in week 2. For every 1,000 joules I have, that's 1 kilojoule. So you take that number divided by 1,000, which is 26.644 kilojoules per mole. And we go back all the way back to my sig figs. This had 2. This had 3. So it should only be 2, which would be 27. So the enthalpy change, delta H, for dissolving ammonia nitrate in water, which is done through dissolving it in a coffee cup and measuring the temperature change, is 27 kilojoules per mole. What that means, and so you'll learn about this in Gen Chem 2, but I'll just tell you about the concept now. What this means is that you have to put in 27 kilojoules of energy for every mole of ammonia sulfate to dissolve it. That's why when you put it in water, the water turns cold. You're taking energy away from the water and it's going directly into the solid to pull that solid apart. That is why, those things feel cold to you. But that is the calculation there. A lot of moving parts, a lot of different numbers. But like I said, definitely the hardest part is just figuring out what is going on. The actual math itself should be relatively simple, I hope, at this point. So don't let yourself get overwhelmed by the math. Just sit down with this problem, start labeling your variables, and work from there. When I divided 416.098 by, I got 26,672. So you got a slightly different number because the actual moles I have go on for more digits because I'm doing this in Excel. So yeah, there's more digits than what I wrote down. That's why we get slightly different numbers there at the very end there. All right, any questions about anything as we wrap up for today? All right, so there's one thing I do want to say that before we let go. Your next test is coming up rather quick. It's April 5th. So it's not this upcoming Monday, but it's the Monday after that. So it's right around the corner. So just be aware of that. All the PowerPoints will be in the test 3 folder. I will talk more about the test next week. For today, I will put up a homework assignment that will help give you more experience. Will we be able to take the test like last time? That helped a lot, probably, in that like you can have your resources, because I can make these tests where you can't look it up on Google. I will say though, do not put my tests on Google. I already caught somebody doing that and I was not quite pleased with that. So as long as people don't post my tests on Google or any of those websites, that's fine. Yes, I hope my resources help. That's the goal. But with that, I have nothing left for you. So yeah, make sure you look out for that homework and I will see people next week. Have a good weekend, everybody.